Welcome everyone to the review slides for the mechanics course, where in this presentation we will review Newton's three laws of motion. We will state each of the laws a bit more rigorously and look at some examples that illustrate each of them in action. Now, each of the laws of motion involve the concept of forces, so before reviewing each law, we'll quickly remind ourselves of what we mean by a force. Forces can be seen as a push or a pull that causes a change in velocity. This change in velocity is a key part of the first two laws. Now, forces can generally be classified into two types. First, there are contact forces. An example of this is someone attempting to move a box. A contact force arises the moment the person presses on the box. This force only exists as long as there is contact with the box. The moment the box is out of reach of the person, the contact force disappears. The second type of force is called a field force, which acts between objects that are not in physical contact. As an example, the force of gravity is a field force, which for a planet orbiting the sun always points to the sun, thereby causing the planet to move in a circle. So Newton's first law of motion discusses what happens when there are no forces. It states, if the net force acting on an object is zero, then A, the object stays at rest, as can be seen by the ball that is not moving, i.e. its speed is zero. Or B, the object moves at constant velocity, which means at constant speed in a straight line, and this is important to note for later. So here we see a ball moving back and forth. We don't see what happens to the ball off screen, but during its motion on screen, the ball is moving with constant speed in a straight line. So for both scenarios A and B, we see no forces acting on the ball. Newton's second law of motion discusses what happens when there are forces. It states, if the external net force on an object is not zero, the object accelerates in the direction of the net force. So the net force, which is a vector, will act in the direction of the acceleration vector. These vector quantities are indicated in the equation F equals ma by the arrows over the letters. Furthermore, the acceleration is directly proportional to the net force and inversely proportional to the object's mass. This can be seen by solving F equals ma for A. We see that the mass is in the denominator, so the bigger the mass of an object, the smaller will be its acceleration when you apply a force to it. We'll see this in a later example. So let's consider Newton's second law for two scenarios. The first one is for a change in speed. An object that accelerates, either speeds up or slows down, is under the influence of a net force. So here we see a ball oscillating back and forth. A force acts on the left side, causing the ball to accelerate to the middle. Once it passes the middle, another force acts on the right side, causing the ball to decelerate. Once it stops, that same force continues to accelerate the ball back to the middle again. So both forces point to the center. The ball speeds up, heading to the middle, then slows down when it passes the middle. This is what causes the ball's oscillatory motion. In the next scenario, we consider Newton's second law during a change in direction. An object that maintains the same speed but changes its direction is also under the influence of a net force. Consider an object that is initially traveling in a straight line at constant speed and is suddenly caught in a gravity well. The force acting on the object is directed to the center, causing the object's motion to become circular. The object's speed isn't changing, but its direction is, and so the object is actually accelerating. In particular, the object accelerates in the direction of the force, which is toward the center of the circle. Hence, the acceleration is called centripetal acceleration, where centripetal means center-seeking. Newton's second law specifically refers to the net force, which is basically the final force that results when you subtract all the forces acting in one direction from all the forces acting in the opposite direction. Specifically, the net force is determined by summing, i.e. adding up, the components in the x and y directions of all the forces. So let's say we have one force labeled Fa acting in one direction. and a second force labeled Fb acting in another direction. Draw the components of Fa in x and y. Do the same for the components in Fb. Now sum all the force components in x, which will be the component of Fa in positive x plus the component Fb in negative x. Note the negative sign in front of Fbx. Because Fa component is longer than the Fb component, the net force in x is positive. Do the same for the force components in y, which will be the component of Fa in positive y plus the component Fb in negative y. Because the Fb component is longer than the Fa component, the net force in y is now negative. We can then draw the net force resulting from forces A and B. Simply draw the x component and the y component of the net force. Complete the rectangle and draw the vector for the net force. To determine the magnitude of the net force, simply square the x and y components, add them, and then square root the result. We now come to Newton's third and final law of motion. Unlike the first two laws, which dealt with a single object, Newton's third law deals with two objects. It states, for every action force, there is a simultaneous reaction force equal in magnitude but opposite in direction. Two key points are that the forces must be of the same type and act between two objects. For example, consider the tire of a car that is driving along a road. There is the contact force of the tire on the road, which is the action force, as well as the contact force of the road reacting back on the tire. So both forces are of the same type, i.e. contact forces, acting between two separate objects, namely the tire and the road. As another example of Newton's third law, we'll consider gravity. All objects exert a gravitational force, which is a force that acts over a distance, also referred to as a field force. We see here two objects of different sizes representing different masses. The gravitational field forces acting between the two objects accelerates them towards each other. This is one example of Newton's third law. At the moment they collide, contact forces accelerate the objects away from each other. This is another separate example of Newton's third law. Now, as soon as the objects separate, gravity again accelerates the objects towards each other, causing the objects to slow down as they move apart, stop, and then speed up as they head back towards each other for another collision. Also, notice how the two objects have different accelerations, as seen by how far each object travels. Why is that? Well, this is a direct result of Newton's second law, which states that the acceleration is inversely proportional to the mass of the object. Remember that under the third law, the gravitational forces between objects A and B are equal in magnitude. So FAB, which is the gravitational force on object A due to object B, will be the same as FBA, which is the gravitational force on object B due to object A. But object B is more massive than object A. So if we divide FAB by object A's smaller mass, object A's acceleration will be much bigger than object B's. This is why the acceleration of the two objects are not the same. Finally, we're going to look at one last scenario. Consider the gravitational force Fg and the normal force Fn acting on a box resting on a horizontal floor. These forces are equal in magnitude and opposite in direction, but they do not represent Newton's third law. Why? Two reasons, actually. The first is that the forces are not of the same type. Fn is a contact force, while Fg is a field force. Secondly, both forces are acting on the same object, namely the box. One way to see the difference more clearly is to tilt the surface on which the box rests. By simply tilting the surface, Fn and Fg are no longer equal in magnitude, nor are they opposite in direction, which they need to be under Newton's third law. So this concludes the review of Newton's three laws of motion. Please send me any questions you may have using Mio or post them to the discussion forum. I will try my best to answer them in a timely fashion. Thank you for your time and take care.